Yes.
Great. So, yeah, I've been asked to give a talk on numerical relativity as well as run some labs over the next few days. So I thought I would just give a brief overview of that first. The labs, you've hopefully received an email from me to log into a Jupyter Hub server on a virtual machine that's being hosted at University of Auckland. So I have not received any emails about this not working, which is great. It's a good start. I don't want to jinx it. At the moment, if you're wanting to log in, it's currently down just because the IT person has decided that it would be good to add a bit more space to the directory where all of your files will be run and data saved. So he's doing that now. So this should be up and running. I'll get it back up and running before the lab time in that break. So yeah, the idea for these labs was to have a way of all of you running it from your own machines without actually having to worry about installations and things like this, which would have been a complete nightmare. So all you should need is a browser and a login, and then you should be able to run the Python code that is there as a Jupyter notebook, where, as you'll see in the lab, next, that we have some sort of fun gravitational wave simulations for you to run, which will be unlike the linearized waves that Jörg has talked about. These will be fully non-linear, but in plane symmetry. All right, so yeah, that's essentially the plan for the next 2 days for the numerical relativity stuff. So why are we interested in numerical relativity? Well, let me just share my screen of this one. So can everyone see this simulation with the full screen?
Yep.
So this is similar to what Jörg had shown earlier, but slightly different. So this is looking at the outgoing gravitational waves of a binary black hole in spiral, where you have the extracted waveform at some far extraction sphere at the bottom, and you have the in spiral in the middle, and the huge amount of gravitational waves that are being emitted. This process is very hard. I mean, analytical solutions are out the window for pretty much this whole process. The in-spiral, the merger, and the ring down after they merge are sort of three aspects of numerical relativity that have different techniques. The in-spiral can be done with these post-Newtonian approximations. Because this was quite a long in-spiral, you don't want to be doing full numerical techniques during that in-spiral. It's very expensive. The merger, like you've just seen there, when it's slowed down, can be done with the full numerical relativity, full nonlinear Einstein equations, all of that stuff. And then right at the end, you have you can see how quickly it sort of dies down, and that ring down at the end is very well approximated by linear perturbation theory. So what Jörg was talking about, where you take Minkowski space and you do a linear perturbation of that, you can do the same thing for a single black hole space-time, which is the end result of this merging process. And the equations themselves are still very hard. If you do it for the Kerr, around the Kerr background, this is called the Tucholsky equation, after Sol Tucholsky, who did the work in the 70s. And it's quite difficult to actually solve these equations. But the linear perturbation theory is very well approximated. Is a very good approximation of the system very soon after the merger. So there is no point in doing the full numerical relativity after that. So that's just a little example of one of the main applications of numerical relativity, and sort of their three distinct parts. Now, this is, of course, in vacuum, but there is also work that's been done, lots and lots of work, on neutron star mergers, where you have matter content floating around, and this makes things way more complicated than the already complicated binary black hole merger, by including the matter fields into the Einstein equations. And I've not been brave enough to do any of these full simulations myself. I've done some binary black hole ones, but not these ones. And so there are code bases that I'll talk about shortly that have the ability to do these simulations with matter. And so this here was a neutron star merger that eventuated in a black hole. So you can see why, if you're studying these things, why you're going to need numerical techniques to be able to well represent these sorts of systems. So numerical relativity is essentially just using numerical methods within the framework of general relativity. There are multiple code bases that allow for the sorts of simulations that you've just seen, which are incredibly complicated, incredibly large. The Einstein Toolkit, for example, is an open source project that utilizes Cactus, and that's a community-driven project that's at least a decade old now, I would guess. And it just gets built upon and built upon, so it's massive now. So these sorts of numerical methods are used when closed form solutions are impossible. So it would be very difficult to write down a function that describes one of those processes or functions. And the binary black hole merger was first completed in 2005 by Franz Pretorius, who did the first full binary black hole simulation. And so it's, that's, well, I guess making me feel a little old. That's nearly 20 years ago now. I feel like that's supposed to be a recent result. Also things like numerical cosmology, going away from, FLRW, which is an expanding universe plus something, to fully relativistic evolutions, has only really begun in like 2015, 2016. So these are things that I know David Wiltshire from Canterbury and Florian Bayer from Otago are interested in. And so this is quite a young field with respect to some of the other applications of numerical relativity. So it's very exciting it's a very exciting field to be in, I think. So in terms of the binary black holes and so on, as you've heard about today, we are able now to detect these signals coming from such events. And what we want to be able to do is to be able to figure out, given an observation, what was the physical process that gave rise to that signal. And what we do, or what others do, because I don't actually do this myself, I just know what they do, is that they do these theoretical simulations where you use the Einstein Toolkit or whatever. You set up two black holes, you run the code, it does the merger, and then a bunch of gravitational radiation is spewed out that is read off in what's called the wave zone, so very, very far away. They read off the gravitational radiation, and that's what is then snapshotted and said, okay, for these physical parameters, we get this gravitational wave signal out. And they do this for a huge amount of parameters, changing the masses, the spins, and so on and so forth, to get a template bank. And then it's a very complicated procedure that they do, which I I don't know much about, but they do some data analysis and they say, okay, well, this is the signal that we've got. This is the templates that we have. Let's put them together and figure out what the physical parameters of the observed signal are, and what was the system that caused that signal. So that's the numerical relativity contribution to all of these, relating to observations and things. All right, so I should, you've seen it already today, but I should put in the Einstein equations, because, this is the set of equations that we want to solve. We want to get the metric of the space-time, and that basically gives us everything that we want to know. And the left-hand side here is the curvature that corresponds to the space-time, and the right-hand side is the energy momentum of the space-time, or the matter content. And so, like Jörg said, these are coupled in the sense that, if depending on which way you think about it, matter tells space-time how to curve, and space-time tells matter how to move, by looking at these from the different perspectives. So at the end of the day, this is an abstract thing. We need to put in a frame and coordinates and so on to end up with a concrete system that we want to solve. And this ends up being nonlinear coupled PDEs, which are quite difficult to solve. And so the numerical relativity is all about putting these equations into a formulation that allows you to use numerical methods and perhaps PDE theory to make sure that your system is nice before you start doing the numerical implementation. So this is what we want to understand, or this is what I would like you to understand over the next few days, is standard methods of solving the Einstein equations numerically, by looking at sort of what formulations of these equations do people use. And then once you've formulated something like the ADM system or the BSSN system, which you'll learn about, how do you actually put this on a computer and solve it? So that's what we'll be doing. So I would like to talk a little bit about numerical concepts and methods first, because that way, hopefully, the lab will make a bit more sense, because you'll be hands-on evolving a formulation of the Einstein equations that is quite well suited to investigating collisions of gravitational waves. So the standard methods that people use for these binary black hole evolutions and numerical cosmology and things like this, they are they're not the best system to study from a mathematical point of view, and certainly from a numerical point of view, they are not really that good. So the system that we'll be using is another formulation that's certainly not as popular, but is one that has nice mathematical properties, which then sort of leads into nice numerical properties. And it's complicated enough that you can look at colliding gravitational waves, and all of the sort of numerical techniques and methods are still there, but it's just a much simpler system. So that's sort of what I think will be the most beneficial. Okay, so at this stage, we just have the Einstein equations, which are a bunch of, once you put in a frame and coordinates, a bunch of time and space derivatives all muddled up. How are you going about solving this? So the idea, the fundamental idea for all of these numerical evolutions is to foliate your space-time by a bunch of surfaces that are usually parameterized by a time coordinate. So the level sets of this time coordinate give you these spatial three surfaces that are submanifolds of your space-time, on which you can sort of think like we do, in most, the way we usually think is, we are experiencing three spatial dimensions at differing times, right? I think that's sort of the natural way that humans think. And so we want to emulate this on the computer by saying, okay, we want three-dimensional spatial surfaces parameterized by a time coordinate. And this is the way that we do all of these numerical simulations. So what does this thinking do to the equations? Well, it ends up giving us two types of equations. The first one is, well, suppose that we fix a time, I should have written these down the other way. I spent most of my week working out how to do the labs. The time equals constant slices, which we can call time slices. So for example, T1 here is parameterizing this surface sigma 1. If we project the Einstein equations onto here, we end up with equations that involve just spatial derivatives because they are intrinsic to this slice as long as you set up your coordinates and so on appropriately. And so if we had a solution to those equations, which are elliptic equations, and in general, solving these constraint equations, which are the projection of the Einstein equations onto these surfaces, they are very complicated. However, suppose we had an exact solution, then we know they would satisfy the Einstein equations. So that would be, they would satisfy the constraint equations. So suppose we had metric and so on that are living on this spatial 3 surface, and we want to say, okay, well, I've got a solution of the Einstein equations projected onto this spatial slice. Now, what about how do I get from this slice to the next one? Okay, so that gives us evolution equations. So given a set of data on one of these slices that satisfies the constraint equations, the evolution equations tell us how the data evolves in time. So as you would expect, this would contain time derivatives. And this is the central part of solving these things numerically, is that we want to take our evolution equations and use a numerical method to approximate what, given data on one slice, what is the data on the next slice. So the evolution equations may contain time derivatives, must contain time derivatives, may contain spatial derivatives. It's not necessary. The system that you'll be looking at in the labs, there are only 2 evolution equations that contain spatial derivatives, so they're PDEs. The rest are ODEs, and they just propagate along constant coordinate lines. The constraint equations, however, must contain only derivatives that appear tangential to these slices. And as such, because these constraint equations, so suppose you labeled one that should be satisfied by C, so that C equals 0 must be satisfied on these spatial slices. This is kind of unique in the sense that the evolution equations, you can add the constraint equations to the evolution equations to change the principal part of the evolution equations and get completely different mathematical properties of your system. So evolution equations are not really unique as opposed to constraint equations. And in fact, there's been a lot of study and research done on how to do this in a way that your evolution system remains as stable as possible for as long as possible. So this is sort of the standard idea of the basis of all these numerical simulations is you have a set of constraint equations that tells you essentially what the Einstein equations are projected onto some initial time, for example, and then the evolution equations tell you how to take that data and propagate it into the future to see how the system evolves. So a natural question I think that arises here is, if you have a solution to the constraint equations on one surface, does that mean that as you propagate that data, the constraints will remain satisfied? So this is certainly true analytically, but numerically, is it true? maybe, does anyone have an idea about whether that would actually be true numerically?
I think it isn't.
Yes. Yes, thank you for being brave enough to answer. It's exactly right, because suppose that you took a time derivative of the constraint equations to see how they propagated. Then the right-hand side of that would be a combination of the constraints themselves. So if the constraints are satisfied initially, then they'll be satisfied for all time analytically. But numerically, of course, you're limited by the precision of the computer. So if you're using double precision, then you might have 15 digits or whatever. You can only satisfy the constraints up to, say, 10 to the minus 15 accuracy. So that small noise that is floating around, suppose the constraints evolved like d by dt on c is equal to c, right? So then you're going to get an exponential when you solve that. You're going to get an exponential with respect to time, and even if c is small initially, if it's evolving like an exponential, then at some point that's going to not be good for your constraint violation. So handling the constraints over time, and especially over long periods of time, is quite difficult. And that's one of the reasons why the first formulation that was implemented numerically, the ADM equations that we'll see soon, that's why they failed, because they were not, the constraints were not playing nicely over long periods. All right, so let's get into some numerical methods to see, given this idea of evolving this sort of time slices, what this looks like on a computer. I will get to the formulation, the standard formulations after this, just in case I run out of time. Then you have the numerical sort of methods in mind for the lab that's coming up. So it's kind of, I don't know, I would almost do it the other way around if I had a 2-hour block now, for example. All right, so with this foliation, we've sort of taken something continuous like our time direction, and we've discretized it into surfaces. We have to do the same thing spatially. So we're going to take this is just a one-dimensional example in space, one in time. We're going to discretize our computational grid, or our grid, into a finite number of points. And we're going to replace, the x-coordinate now, which is a continuous function, with a finite set of points, the xj, and do the same thing for the t. So our functions now, instead of being continuous, become discrete, and they are defined on these points here. So the idea, firstly, is suppose that we had PDEs that we were evolving, and they had spatial derivatives. So if you were calculating ordinary differential equations, then you don't need to do this, and you can sort of use something which I'll explain in a moment, like Euler method or Runge-Kutta-4, that you might be familiar with, to evolve your data in time. But if we're wanting to evaluate anything that propagates, we're going to need spatial derivatives at some point. So these are, of course, continuous derivatives as well. How are we going to take this and make this discrete? Well, one very nice way of doing this is doing Taylor expansions, which you might have done these calculations before in a third or even a fourth year sort of numerical analysis course. But the idea is you take some function, and as long as it's analytic, then you have the Taylor series will converge in the neighborhood. So if you did this Taylor expansion around some point A, then it looks like the following. And what we do is we do it up to a certain number of points, a certain number of terms, and then we truncate it. So what we can do is, suppose that we were looking at this at a fixed time, and that's what we would be doing in a numerical simulation. We would be fixing the time to be, say, 0. We would be evaluating the evolution equations at that time and using that information to propagate forward in time. So we'll fix our time, and we'll pick that we're doing a Taylor expansion around xi, so some the ith point, and we're going to evaluate that expansion at a neighboring point I minus 1. So just putting that into this formula here gives the following, where the dx is just the difference between neighboring grid points. So that would be the step size, spatial step size of your discretization. So it's, xi minus 1. So you get this approximation here. Now, what we're wanting to do is we're wanting to try and get a formula for the first derivative, the first spatial derivative. So what we can do is we could obtain another equation by doing exactly the same thing, except expanding about xi plus 1. So we get the following formulae here. And so you can see that we can, there might be some sign errors here. The idea is, if you write this down properly, and I think there must be some sign errors there, and you do the following linear combination of these expansions, then, so if I do fi plus 1 minus fi minus 1, so the second derivatives, for example, should have the opposite sign, and so should the fi. Then what you find is that the f prime doesn't drop out, but you get twice, so you get a 2 that gets divided by, and the idea is that you have an approximation for the derivative of your discretized function at the point xi in terms of the function evaluated in the surrounding points. So this idea is called finite differencing, and you'll notice that there is an order here that is floating around. So this is third order, but when you do this multiple times and so on, this is called a second order equation when you add up all of these things. So basically this is just a method for finding the derivative at a point based on neighboring points by just using a simple Taylor expansion. There was not a lot of thought really involved in that. And the nice thing as well is that you can do higher order derivatives. So all you do is you do your Taylor series and truncate it at a later point. And then you can also, add and subtract them evaluated at different points and so on to find the first derivative or even higher derivatives based on more points, but you have a better order in here. So in particular, for example, the fourth order method would require, I think it's instead of 2 points, you have 4 points. So it requires a bit more work to be able to evaluate it, but as you decrease the dx, then the power here will be larger, so you'll be getting a better error. The error will drop quicker as you increase your spatial resolution. Further, one thing that sort of stands out is if your grid looked like this, you'll notice that this is what's called a centralized finite difference operator, because it's centralized around a particular point. So if I wanted the derivative at this point, can you see my cursor, by the way?
Yes.
Yes.
Okay, good. So for example, if I wanted to take the derivative here, it would require the function evaluated at the neighboring 2 points here and here. But what happens if I want to take a derivative at the boundary? I can't do that. There are a couple of ways to do this, but one that I'll note is that you can in fact use what's called one-sided finite difference operators. So these are that if you're wanting to take a derivative at the in my case, the right boundary, then it is in terms of points on the inside only. So you can get away with that. Another way to do it, which I'm not getting into, is to use ghost points, which is you have sort of some fictitious point that is outside of your computational domain, but you know some information about f there, and you can continue to use your centralized finite differencing operator there. So for example, tomorrow when I talk about some advanced techniques like parallelization, you will see that you can split your grid into certain parts, and neighboring points might appear on another grid, in which case you can just use your regular centralized finite difference operator on an internal boundary. So this is a simple sort of overview of how you would take a derivative of a discretized equidistant grid. Now, at this point, we would have our evolution equations. So, for example, we have dt by dt on f is equal to something. If that something is algebraic, we can plug in our initial data that we know satisfies the constraints. If the right-hand side involves spatial derivatives, then we can approximate them using finite difference operators. So at the end of the day, we end up with a right-hand side, which is numerical. So we have numbers for the right-hand side of this thing when it's discretized across this, this spatial slice. So at this point, what we can do is we can say, well, we can just use a simple thing like Euler method or Runge-Kutta to approximate the time derivative to go from t equals 0 to t equals 0 plus h plus a small step, right? And so this, so Euler method is essentially the same sort of principle as the finite differencing. It's just a Taylor expansion up to linear order in time now, and that is used to approximate the next time in terms of the previous one and its derivative, which is the evolution equation. More complicated ones like Runge-Kutta, which are a higher order, can be used, and these are the standard. Runge-Kutta 4 is really the standard numerical integrator for things like binary black holes and that. And I don't think I've ever not used it except maybe for testing purposes. But for example, I know that the Euler method coupled with the BSSN equations, which we'll get to at some point, which is a standard formulation of the Einstein equations, is unstable, but Runge-Kutta is fine. So yeah, Runge-Kutta is great. All right, so one other thing that I won't go into too much detail about, I will just mention, is boundary conditions. So if you have a PDE which is propagating, so for example, if you have a single advection equation or something like this, then it has a one mode that's propagating, and it will be propagating in one direction. And the point is that if you've discretized your grid already, and you've got it like this, and you have that on say the right boundary, if your equation has a characteristic which is moving from right to left, then on the right boundary you need to specify what's coming in, because the computational domain is not out here, and so it doesn't know what's coming in, and that needs to be specified. On this side, if the wave or whatever was propagating from right to left, it's leaving here, so there's no additional information that needs to be set here because it's leaving. But on the boundaries where stuff is coming in, you need to tell the numerical system what is coming in, and so you need a way of what's called imposing boundary conditions. So there are multiple ways of doing this. I have the most experience with this simultaneous approximation term method, or the SAT method. So essentially what you do is you add a term to the evolution equation that is describing this propagation, and you add a term on the boundary that involves the data that you want the function to have on the boundary. So the boundary condition is like, I want u to be sine of t on the boundary. So what you do is you add a term into the evolution equation that's just changing the boundary point. And what it will do is you do it in this, it's quite involved, so I won't go into details, but it basically drives the variable towards the value you want through this modified evolution. So it's found that, you know, plugging in boundary conditions to the system itself. So you could just say, well, if u is something that is propagating and it needs a boundary condition, why can't I just put u equals sine of t on the boundary and then not do anything fancy there? Just don't evolve it. That sort of thing is known to be unstable. It may work, but a lot of the time it doesn't. And so this is a way of sort of doing it in a more subtle way, and this is proven to work very nicely for the systems that I've worked on. So this rigorous analysis that I mentioned at the bottom here of the characteristics is for first order systems where you look at certain you basically take all of these coupled equations that contain things that are propagating, and you do some change of variables and so on, and you find a new system which has decoupled all of these things. And that allows you to sort of say, well, okay, this is the decoupled modes. These three are going in, or, you know, these are the directions of these three, and so on. And that allows you to figure out what data is flowing in at a particular boundary, and then that tells you that you need to specify conditions for those. So just the fact of trying to take some first order system of PDEs that are not elliptic, hyperbolic or something, and trying to figure out what's propagating in is actually sort of non-trivial. So I just wanted to mention this, that boundary conditions, imposing them are not straightforward, especially with standard formulations. They do some wacky things to make it stable, which I'll talk about probably tomorrow. Okay, so the other thing that I really wanted to mention today, and this is what you'll be doing in your labs, is to make sure that when you've implemented all of these spatial derivative operators, you've implemented your Runge-Kutta 4 to evolve your space-time, you've done all of this discretization and all of that, and it works, oh great, I've implemented this on the computer, I've run it and it didn't crash and I have some output. You need to be really sure that your output is correct. So there are lots of ways of doing this. A nice way, for example, is to show that when you increase your resolution, so as you have finer and finer spacings between your grid points, that you approach an exact solution. So you might be lucky enough to say, well, I have this exact solution, so if I put in the initial data and the boundary data that would represent that exact solution, I should, in the limit as my grid points get closer and closer together, I should approach this, this exact solution. So for the Einstein equations, we have constraint equations, which are a really nice check because they need to be zero everywhere at all times. So when we're doing these evolutions, what we can do is we can check the constraint equations on each time slice and see how well they're satisfied. But it's not just the satisfaction of the constraints that are important. It's the fact that as we increase our resolution, these constraints should be better and better approximated. So this is what's called a convergence test, is you want your constraints to converge to zero, and importantly, you want them to converge to zero at the correct order. So, for example, if my code is using a second order finite difference operator for the spatial derivatives, and I'm using Euler for integration in time, then this should be second order. So what this means, and this will be explained in the lab, is that as we, or it can actually be seen pretty straightforwardly by the power of the piece of the Taylor series that you're truncating. As that gets larger, it's obvious that as you take your dx, or your interval between your spatial grid points, to be smaller and smaller, the error is going to go like that, that difference to the n. And so obviously, as you've got a larger n, as you say double the number of grid points or halve this, then it's going to go down quicker. So not only is are your constraint equations needing to be shown to converge to zero, but to be rigorous, you should show that they're converging at the order that is predicted by the numerical techniques that you're using. So that's what you'll be doing in your lab this afternoon, or very shortly. So I really like to use this as an example. This is something that I did during my PhD with Jörg. This is a situation where we have a black hole, and we're going to shoot a gravitational wave into it, all numerically, of course. And we were wanting to check the constraints to make sure that they converged. So what is this? I'm plotting log base 10 of the error, which is the constraint. This should be 0. This is over a radial slice. So we were doing it in axisymmetry. So there's an angle here. When we fix an angle, we get a radial slice. And the numbers here represent the number of grid points, or actually the number of intervals between our grid points. So as we increase our radial resolution, which is, this is the radius here, we should hope that we would get a better satisfaction of the constraints. So what you'll notice here is that on this is all random noise, because we're at 10 to the minus 15 in a log base 10 plot. So this has actually hit the floor of the precision of the doubles that we were using. So this is because we were using an exact solution here. So this is at a given point in time. We're looking at across the entire radial grid at that point in time. On the right-hand side, what we do is we use our boundary conditions to have a non-trivial data for the ingoing mode that is actually a gravitational wave. So we use some sort of sine profile on the boundary to give some bump, and that will propagate into the computational domain. So that's why things are going being non-trivial here. So what happens when this is very early on, because most of the simulation is still the initial data. So what happens when I go and look at this plot at later and later times, right? So there's clearly something not right here, right? That's why this is a bad boundary data. So you can see that here, it looks like as we're increasing the resolution, we are going closer and closer to 0. So this looks good, right? Here, not so much. As we increase the resolution, the satisfaction of the constraints is not getting any better, right? So that's something that's not good. And what's interesting here, just to remark, is that the wave, it's a gravitational wave, so it's traveling at the speed of light. The wave is actually slower than, is traveling faster than these errors, right? So if you see it, the errors are propagating in from the boundary, but they're propagating slower than the wave. And in fact, you can show by looking at the constraint propagation system. So this is a system that looks at how the constraint variables, which should be zero, how they evolve with time. If you did an analysis of that PDE system, you would find, in fact, it has an ingoing mode on the boundary as well. And if you don't choose your boundary data correctly, then this non-zero mode will propagate in from the boundary and make the constraints non-zero. And we found that, in fact, this constraint violating mode was traveling in following a time-like direction, so it was lagging behind the wave. So what we did was choose boundary conditions in such a way that this ingoing mode was zero, and looking at the exact same situation but with this boundary data, we could see that over time we were getting much better convergence, or convergence to zero. So this is what we would like to see. This is showing that the constraints are across the entire radial grid in this case. As we increase the resolution, the constraints are approaching zero, up down to machine precision. And it's, of course, the difference between these curves has information about the order of the method. And that's something that you'll plot in your labs this afternoon. So if you're reading someone's paper that do this sort of numerical evolution and they don't have convergence tests, then you should be very skeptical, because they are really necessary to validate your results. Okay, so that's what I wanted to get through. I will make a start today before the lab on an actual formulation of these Einstein equations. So you have the idea now that you have this foliation, you have evolution and constraint equations, you have a very rough idea about how the numerics work. Now, how do you actually, what are the evolution equations and what are the constraint equations for the Einstein equations? Well, there are many different formulations, but the first formulation was the ADM, which was named after these three gentlemen here in the late 50s. And the idea is essentially to project the four-dimensional space-time quantities onto these spatial surfaces and use quantities that are intrinsic to these spatial surfaces. So instead of using four-dimensional indices, you'll be using three-dimensional indices. Instead of using a four-dimensional Riemann tensor, which represents the curvature of the four-dimensional space-time, you'll be looking at the three-dimensional one given the three-dimensional metric and so on. So that's the idea of doing this. There are also gauge quantities that are necessarily introduced, because in doing this foliation, you have to specify how you split your space-time into these different surfaces, and how do your spatial coordinates propagate when you go from one time slice to the next, and so on. And these are given by the lapse and shift. So the lapse and shift functions are the ones that were in Jörg's video with the binary black holes with the color and the arrows. The color was the lapse, which represents some sort of proper time between surfaces of constant spatial coordinates, and shift is a three vector that sort of corresponds to how your spatial coordinates move from one time slice to the next. So these are completely gauged, because how we foliate our space-time is up to us. It's independent of the Einstein equations. But the rest, the Einstein equations, will tell us how everything else propagates. So, like I said before, we have a 4D space-time, and we're going to foliate it with 3D hypersurfaces. And if these are parameterized by some coordinate, so say we have a coordinate t, then the four-dimensional covariant derivative acting on t, the level sets, or that this will give us the co-normal to the surface, and that will give us an idea of, well, maybe we want to propagate in this direction, because if the surface is space-like, then the normal is going to be timely. So we introduce this co-normal to these t equals constant surfaces, capital omega, and this is just the direction that's important. What we want to do is we want to define the lapse to be related to the length of this normal, and we can do that by just saying that the metric transvected with this omega twice is given by this here. And this is the lapse that we'll be talking about in more detail later. And given this, we can define the unit normal by n upstairs a by this. So we're just going to raise the downstairs index with the metric, multiplied by minus alpha, and you can tell pretty easily here that the inner product of n with itself is 1 with respect to this metric, minus 1. So in particular, I should mention as well that I'm using the normal conventions where minus 1 will point in the time-like direction and positive numbers point in the spatial directions. And this derivation is largely following this book called Solving Einstein's Equations on the Computer by Baumgart and Shapiro, I think, if I pronounce that correctly. Okay, so now that we have a normal to our foliation, what we want to do is we want to use that to try and project these four-dimensional quantities that appear in the Einstein equations to be quantities that have no component in this normal direction. So they are intrinsic to the orthogonal directions, which are these spatial surfaces. So what we can do is we can define this gamma AB here, which is thought of to be the three-dimensional metric induced on this spatial slice with normal conormal n. We define it like this, then it's clear that this gamma has no normal component, because if we contracted it with two n's, we have that here we have GAB NANB, which from the previous slide was -1. Here we have NB, which is -1 times -1, which is +1, so that vanishes. Similarly, if we contracted this gamma with a spatial vector and a normal vector, so a spatial vector is one which is orthogonal to our normal vector, then we find just again by a similar calculation that must also vanish. So that means that gamma is completely intrinsic to this three-dimensional surface and does not have any components in the normal direction. So this gamma is actually used as a projection operator, that if you contract a four-dimensional tensor with this gamma, you will end up with the parts of that tensor that are intrinsic to the surface. So that's the idea, is that we're going to project the Einstein equations down onto the surface. But in doing so, we do lose information, which is obviously information in the normal direction that we want to keep. So how do we get around this? Well, in particular, the Riemann tensor, when we project down, we're going to lose some information. But we can represent the remaining stuff in terms of what's called the extrinsic curvature. So together with gamma, the extrinsic curvature is the other variable that's going to be eventually evolved by this system. And the extrinsic curvature is a way of measuring the difference in sort of, it's the way of how the spatial slice is embedded within this four-dimensional space-time, and how the curvature changes sort of as you go away from the surface. So it does that by looking at the differences of the normal vector infinitesimally. So this is given by, whoops, I've got an extra bracket there. This is the symmetric part of nebula CND. So the round brackets here mean it's symmetrized. and we project that down. So each four-dimensional index is going to be transvected with the gamma, and that will then mean that this object here is purely spatial. So this can be also computed nicely in terms of the Lie derivative of the 3-metric along the normal vector. So together with the 3-dimensional Riemann tensor, the extrinsic curvature gives us everything we need to reconstruct the 4-dimensional one. All right, so we also have to worry about the right-hand side, which is not as bad, because we don't have to worry about, things like this happening. We have basically all the different contractions of n and gamma with the energy momentum tensor, and we just define those as certain quantities. So we have rho s in its various forms. And so contracting the Einstein equations with the certain projections, so we can take the Einstein equations and we can project, we can take different transvections with n or with gamma or with different combinations. This will give us the Einstein equations either projected onto the surface or projected in the normal direction and things like that. And these different combinations will give us either the constraint equations or the evolution equations. So if we project so that the Einstein equations are evaluated intrinsic to the surface, we get the constraints, which are commonly known as the Hamiltonian momentum constraints, given by these here respectively, where this capital D that is now appearing is the covariant derivative, the 3-dimensional covariant derivative intrinsic to that slice. R is the Ricci scalar, the 3-dimensional Ricci scalar, and K is the trace of the extrinsic curvature. So that is the constraint equations for the ADM system, which must hold on each slice for that data on that slice to represent a solution of the Einstein equations. Now, I think I'll stop there. The next part would be looking at the projections that give rise to the evolution equations and how we talk about the gauge between slices. So I think that's quite a nice place to stop, and I'll continue with this derivation tomorrow.
Okay, thank you, Chris. I was just about to say that you start taking away time from yourself. Yes, so I guess we have scheduled a break until, oh, I forgot, 4 o'clock or 3:45?
3:45.
3:45. So the labs are, I think we'll keep them very informal. So I think, Chris, you chair this session yourself, because you're basically explaining how things are supposed to work, and we leave it completely open. And so if there are any questions from you guys about any problems that come up in the numerical things, then you just talk with Chris, and I will, or all of us will stay outside. So this will be entirely, amongst yourselves.
And I should mention, there's just a small thing that you guys have to follow to get it set up. So I'll the Jupyter Hub is down at the moment because the guy was adding some more space. So when it's 3:45, I'll share my screen and go through the one command that I couldn't figure out how to do for you. That just pulls the lab files, and then it'll have a PDF with the instructions, and I'll just be hanging around, happy to answer any questions about the lab.
Yeah. In the meantime, if you have questions about anything that Chris has talked about, then also now is the right time to ask that. But if that is not the case, then we'll just wait until the Jupyter Hub opens.
Yeah, which I have to do. I'll do that now.
Okay.